Hi, welcome back to CFD Simplified. In today's video, we are going to explore one of the most fascinating phenomena of fluid dynamics, Bénard cells. A beautiful pattern in which fluid is heated from below and cooled from above. Let's explore how and why it happens and how to simulate it. So we have done the introduction part. So now let's move on to the simulation. All right. So Bénard cell has been given as a tutorial in the OpenFOAM tutorial, so we don't have to make a case. It is already present. So first we will go into the OpenFOAM tutorials and we'll copy from there. Okay, so we will open foam tutorials, then we will go to heat transfer, then we will go to buoyant Boussinesq pimple foam. You can see that Bénard cells are here. Okay, so I have already copied the whole heat transfer tutorial, okay, uh, to my home directory. Okay, so let's go there and we will just move on. Okay, so those who don't know how to copy, so I will tell you that you can just uh, yeah, so if I wanted to copy whole heat transfer, then you have to press cp minus r heat transfer, then give your home, the directory path basically where you wanted to copy this the tutorial. Okay, so this, like this, you can do it. Okay, so I'm already copied, so I'm not pressing enter. So I'll just press cd to reach our home directory. This is my home directory, and you can see that heat transfer directory is here. Okay, so I will just go to heat transfer, then I will go to buoyant Boussinesq pimple foam, and here I will find Bénard cells. Okay, let me clear the uh, screen. Okay, so yeah, it is here. Clear the terminal. Okay, yeah, so we will go inside Bénard cells. Here you can find zero consonant system. There is no all-run file. Okay, if there is no all-run file, what you will do? Don't worry, you wanted to check about what steps we have to perform. Okay, like for example, first we have to go for the block mesh or not. Is mesh is already given, then we have to go for snappy hex mesh or not, or it is required or not. Okay, then we have to go for decompose par or not, or some other commands. Then we have to go for the solution one, like the solver command. That is the thing. So if all-run file is not there, then you can simply figure it out. Okay, like in many cases you must have seen in our tutorials only, you must have seen that all-run files were there. But if it is not there, then how to figure it out? Okay, you can just go inside the system directory, and here you can find. Okay, so here only one block mesh dict is being given. Okay, so what you have to do, and not any other dict is being given. Okay, control dict is like only to control the simulation. Okay, so yeah, you only have to do, you have to run block mesh, and then you can directly jump onto the solver. Okay, you don't have to run. If snappy hex mesh were given, for example, then you have to run after block mesh, you have to run snappy hex mesh. If parallelly simulation is being done, so decompose particle must have been given, so you can just use it. It must be there inside the system directory, so you have to run after block mesh tick, you have to run decompose particle, and then you have to run the solver one. Okay, so here nothing has been given, only block mesh tick is there, and after that we will jump onto the solver. Okay, so just to run the this one, so we will go to block mesh to make the mesh has been completed. I will again clear the terminal. Then the solver is this one, buoyant Boussinesq pimple foam. I'll just copy this one. Okay, copy this one and right click to paste. This remove this forward slash, press enter. Okay, so now the simulation has started. It will only take some 10 to 20 seconds to complete. Yeah, it is completed now. Okay, so yes, let me once again clear the terminal. Yes, Okay, so we have the different time steps. On different time steps the results have been written. Okay, so before we continue, if you are working on a CFD, OpenFOAM or engineering simulation project and need personalized help, I now offer paid support and consulting. Whether it's setting up your case, debugging issues, or developing custom solvers, I'm here to help you move forward faster and more confidently. Just reach out via email in the description. Let's make your project a success. So let's see the results in ParaView. So for seeing the results, we have to first make a .foam file. Okay, then we have to go to paraview.exe foam.foam. Enter. It will take 1 or 2 seconds to open. Yes. So we have our domain with the results. Okay, so first we will go to the solid color, and so this is the domain basically. We can say a rectangular box type domain, not a very typical one. It's a very simple domain, okay, which can be made by using block mesh. All right, and if you just go to the wireframe, you can see the mesh. So what they have done is like, they have made the lines in the x and y. If you can go see the front and back, okay, but in the you can see in the top faces only vertical lines are there, in the bottom face only vertical lines are there. Here also you can see that only single lines are there. Here also you can see a single one dimensional lines are there. Okay, I don't know why they have done that. Okay, I don't know why they have done that. uh, I mean, don't know means like you can do it by like simply we do in normal simulations. Okay, like simply we do in the normal simulations. Like we give the an x and ny. We always give that. Okay, so let's go and check the block mesh dict basically what is there. So again we have to go to heat transfer ct heat. Okay, so we will go to heat transfer, and again we will go to buoyant Boussinesq pimple foam. Then we will go to Bénard cells. Then we will go to system. Okay, and here you can find the block mesh dict. Okay, so here we can see that they have given uh, in the vertices you can see that only simple coordinates are given, and they are in in the many coordinates they have given. In the y1 they have given 0. Okay, so this is basically, this one is representing the 0 is representing here only. Okay, so that is the thing. Okay, and here you can see blocks have also been given. So it will be like 0 1 2 3 4 5 6 7, and simple grading. All right, but yeah, you can make that one also, and like normally we make and then we can have the solution. All right, so yes. Okay, let's go to the paraview again, and here you can see the temperature. We will go to surface. Okay, again it is like the results are coming like this. You know what, let me close it again. You know why there is this legend is coming, like starting from 300, then again going to 300, and in between. Uh, okay, let's focus on the results. I'll rectify this one later on. So here you can see that the alternating, if I'll go to the last time step, you can see that alternating hot and cold regions have been formed across the domain vertically, and these are looking like hexagonal or roll like formation they are just making, okay, depending on the geometry part. So initially we, like if we'll go to the first one, so initially it is like the will observe the smooth temperature gradients, and after that we start having the wavy like temperature. You can see that wavy like temperatures have been formed. Okay, so let's go on the velocity one. So this is the velocity. Initially it is 0 or very very small. You can see that 0, or it is like 0.005, but when time, if we'll just press, so with time you can see that symmetrical roll like structures have been formed, and these roll like structures are basically the hallmark of the Bénard cell convection. Okay, circulating flow cells. All right, it's very beautiful. You can just play it once again. Yeah, okay, so it is like that. Another is like the alpha t. It is basically representing the turbulence. So you know, if we'll go to the last time step, it is already there. You can see you cannot see much turbulence. So basically, like, okay, here I think they are using going with the they've given the boundary conditions of with k and epsilon also, but I think that they are using laminar only, but because it's very small or zero, it's almost to zero into 10 to the power of minus 38, it becomes like it is zero only. Okay, so basically it is they are using the laminar. Okay, so that is the thing. All right. Another is like let's go to the p pressure. So here you can see that the pressure is, okay, so it is basically showing a linear gradient due to the gravity. And PRGH, if we talk about, so PRGH is basically the, you know, RGH means rho GH. Okay, so it is basically the, you know, pressure for buoyancy correction. All right, so it is reflecting the local pressure variations due to the flow. Okay, like the flow is happening, so because of that, how the pressure variation is happening locally, so that is basically it is giving, okay, small differences between. Okay, so this is the thing. All right, so let's go back, and if you can play, and you can find, yeah, as the flow is increasing, you can see that local pressure difference it has given. All right, again you can see a wavy like structures has been formed. All right, so yeah. And one more thing are there, one thing they've given, you must have seen in the system directory, which I opened initially when I've opened. So they've given the system directory. So in the system directory, you must have seen streamlines, one file they have made. Okay, streamlines. So here they have given to visualize the streamlines. So let's open the streamlines. So we will go to this one, open, and we'll go to post processing, sets, streamlines, and here they are. So I'll go to 500, open this track VTP, let's apply. Okay, let's close this one. No, it was solid color, or you can go to the temperature, or you can go to the wireframe. So here you can just uh, this there points. Yeah, yes, it is there. You can see that these are the streamlines you have got. Okay, so you can go to this one, like another time step. Go back, let's go to 700, press OK, apply, close this one. Here also select points. Yeah, so at 700 you can see the streamlines are here. Okay, so if you'll just go and place the surface or go to the wireframe, so here you can see that streamlines have been formed. Right, it's a good visualization. Good visualization. Okay, yes. Alright, so this was the assimilation part of the Bénard cells. Okay, yeah. Bénard convection is not just visually stunning, it's a gateway to understanding more complex natural convection problems in engineering and nature. From weather patterns to cooling systems, these fundamentals apply everywhere. If you found this tutorial helpful, don't forget to like, share and subscribe to CFD Simplified. Drop a comment below if you want us to simulate other fluid dynamics phenomena. Thanks for watching.